So really at that point, that's enough from me on introduction. And at this point, I'm going to be going to hand over to Professor Jin Sun from the University of Edinburgh, who will be talking about one of the projects on basically looking at the formulation of high solids materials. As soon as you go to high solids, a lot of your rules around viscosity and so on break. And this is where there was a need in this area to try and make this formulation of high solids materials more repeatable, more predictable, more reliable. And that's what this project is focused on. So at that point, I'd like to hand over to Jin. So hopefully, Jin, you are online there.
Yes, I'm ready. So
great. If you want to share your screen, you should then kick mine off.
Okay, can everyone see my PowerPoint show?
Yep.
Okay, great. Good morning, everyone. Thanks, Simon. So first, I'd like to thank Simon, Phil, and Helen for their enormous efforts to make this happen. So I really appreciate the opportunity, and it's a pleasure to present some of our research findings in the project of high solid content dispersion. So this is a rather long title, but I thought it's important to emphasize our ambitious goal in the project. We would like to go beyond idealized model system and to go beyond simple flows in a rheometer. So this project is led in Edinburgh by myself in engineering and John Royer and Wilson Poon in physics. We also collaborate with Mark Hall in Strathclyde. We also work closely with 6 industrial partners, as you see in the bottom of the screen of their logos. So the PhDs and the postdoc researchers in this project are really the driving force behind the scene. So we'd like to first acknowledge their contribution, and we'll show some of the highlights of their research. So first, so what is high solid content dispersion? So I'd like to give you an example that we could encounter in our daily life, mixing cornstarch with water. So this is some experiments we can still do in lockdown. So cornstarch has particles of about 10 microns inside. So this is an important number to bear in mind. So if you mix cornstarch with water to a point that it's become difficult to add more dry powder, so the resulted paste can still flow, as you can see from the video, if you pour it slowly. But if you probe them or push them hard with force, they actually behave more like a solid. As you can see, they have fractures and so on. So this type of strange behavior actually turned out to be very common for this type of very dense dispersions, the mixture of liquid with solid particles. And also this type of very dense dispersion with particles relatively large, about 10 microns, are actually very common, widely encountered in industry in forms of slurries, sludges, and paste. So some examples like drilling fluid that used in gas and oil industry, or paste used in catalyst production, and also the paint itself. So these are all mixtures of solid particles with some type of fluid. So in all this diverse application across very different skills and across industrial sectors, so a common goal is to actually maximize the solid content in this dispersion, but still would like to have them flow in complex geometries. So this turned out to be very difficult to formulate this type of dispersion and also control their flow. That's because a tiny change in the particles or in the flow conditions can lead to very large fluctuations, even jamming. So to tackle this very challenge topic, so our project logic is to first study model system, but with realistic features. So to study the rheology in relation to their particle properties, and then to connect the rheology to the industrial complex process in terms of predicting the complex flows. So after we validate this type of process, the model and theory we establish in this process, so then we can provide principles for formulation of this material in industrial settings. So this is the whole logic behind the project. So in today's presentation, we would like to highlight some of our research outcomes in 3 areas. So well, first, we would like to show how we link the particle interactions to the rheology of this type of high solid content dispersion, especially for very nonlinear rheology like shear thickening. And then we would like to expand this to the area where there's not only one type of particles, but particles with different sizes and different interactions. And then finally, I'd like to show some cases we actually can use this rheology to predict more complex flows, such as extrusion and so on. So the color coding here will also be used in the transition slides later. So at this point, I'd like to actually hand over to Dr. John Royer for him to first give some of the research highlights. So we'll stop sharing and
all right. Thank you, Jin. So to understand how dense suspensions flow, we first have to understand where they don't flow. So what I'm plotting here is this relative viscosity of a suspension versus the volume fraction or concentration of solid particles. If we look first at the black curve, we see that the viscosity increases and then diverges around 64–65%. This is random close packing for frictionless spheres. Now, the idea that the viscosity of a suspension diverges at some critical point or some jamming concentration has been around for a while, dating all the way back to Krieger and others in the 50s and 60s. What's been relatively new in the area within the past decade or so is this understanding that if you allow for frictional contacts between your particles, this can shift the jamming point to a much lower volume fraction, this phi m down here shown in red. And with this 2-branch framework, we can now understand a lot of the non-Newtonian suspension flow through as transitions between these 2 different limiting branches. For example, with shear thickening, the way this comes about is if you have particles where they can transition from frictionless particles to frictional particles under increasing stress. This is equivalent to saying that there's some critical compressive normal force that you need to push particles into frictional contact, to break through some repulsive barrier. And what this gives is a viscosity that increases once you're above a stress scale, that sigma star that's set by this force scale, and you smoothly go up from your low viscosity on the lower branch to the higher viscosity on the higher branch. This stress-driven shear thickening that you get in this framework can be described by an analytic model due to White and Cates, where your jamming volume fraction is now a function of stress, interpolating between your two different limiting values, controlled by this function f, that's your fraction of frictional contacts. And this type of framework can describe experimental shear thickening data very well. This is shown here for silica particles in some solvent, but this type of behavior is very general and observed in all types of suspensions. So what this new picture gives us is it places contacts and force networks at the core of the suspension flow. So what you see here is a snapshot or a movie, I think it's just a snapshot of particles in a suspension colored by the force on them, and you can see the yellow regions are these regions of high force. So this is telling you that you have this very heterogeneous chain-like force distributions. The shape of your force distribution actually quantitatively resembles the force distributions that you get in dry granular materials, and it actually sets the shape of this function, this fraction of frictional contacts f, which happens to have this exponential-like shape independent of your suspension volume fraction. There it goes. So there it goes. So you can see that these force chains, these high-stress regions, are very heterogeneous, both in time and in space. So this new way of looking at wet suspensions through this dry granular viewpoint is really helpful for understanding things like shear thickening. And what we want to do in this project is take this picture and run with it, see what we can do to understand, predict, and control suspension behavior. So one of the first things we want to look at is how we can control the onset of thickening through the particle repulsion, because we've seen how this force scale sets the stress scale for turning on frictional contacts. So we can do this in a suspension of charge-stabilized colloidal particles, 1.5 micron silica spheres in an aqueous solvent. The nice thing about charge-stabilized particles is that you can tune the interaction just by adding a little bit of salt. And so that's what we're going to do here. We're slowly increasing the amount of salt in the suspension. And you see, as we increase the salt concentration, the limiting values, but the low stress and the high stress values of the viscosity don't change very much, at least nothing all that systematic. But you can see that the onset stress changes quite significantly, decreasing by about an order of magnitude as we're changing the salt from less than a millimolar up to around 200 or so millimolar. So we naively expect the repulsion to be decreasing as we're increasing the salt, because we know that if we put too much salt in, eventually we get rid of the repulsion and our stuff starts to aggregate. But we want to be a little more quantitative here. So what we do is a combination of DEM simulations where we can put in known force scales for turning on friction and measure how that changes the thickening onset stress, and then combine that with direct AFM measurements of particle interactions. The reason we need these AFM measurements is because idealized models, such as your DLVO model, fail close to contact at these very small separations due to things like roughness and heterogeneities and things like that. So if you want to get the forces just before contact, you need to be measuring these directly. And we can put all of this together and find that we can quantitatively capture the change in the onset stress with these the forces that we measure from the AFM and the scaling that we get from the DEM simulations. And so you can see that the red is the onset stress we measure from rheology. The black is what we would predict based on the AFM measurements and the DEM simulations. They track each other very well. And right at the point where the onset stress seems to vanish, this is where in the rheology we begin to see shear thinning and yield stresses emerge. And this matches very well with when we begin to see attraction in the AFM measurements. So speaking of attraction, we can now ask, what do we expect, what happens when we add adhesion to these these dense suspensions? And by adhesion, I mean more than just your colloidal U of R potential interactions, but real solid-solid contacts with a finite contact area. And what we find here is that we get something that maybe is a little more familiar to the type of dispersions and suspensions that people work with in industry, where you have shear thinning or a yield stress that gives way to in these that changes with volume fraction. So what you see here on the left is your yield stress measured from steady state flow curves. And this is shown in the black symbols on the right here, diverging at some volume fraction. But if you, instead of doing these steady state flow curves, if you oscillate your suspensions back and forth very gently, you can measure a separate yield stress that is much lower than your steady state yield stress. And this diverges, this oscillatory yield stress, shown in blue, diverges at a much higher volume fraction, very reminiscent of the behavior we saw with the viscosity with those two branches. And the physics here is what you're doing is by oscillating your suspension back and forth, and this is something that Jin will come back to later, you're breaking the frictional contact network. So in one case, you're getting a yield stress that's controlled just by the attraction, but in the steady state, you're getting a yield stress that's actually controlled by attraction and your frictional contact network, and so that it's controlled by phi m instead of phi RCP. And this difference here reveals the importance of friction in these yield stress granular suspensions. And this has been described by a paper by James and Wilson and other people in the Journal of Rheology. And this is sort of tackle this in a general constraints-based framework. If you allow for two different types of constraints that control the way that restrict the way particles move, with two separate stress scales controlling how these constraints are turned on or turned off. So the picture is that if you have something like adhesion, which would constrain rolling, that gets these constraints get broken above a stress scale sigma A, then this gives you your yield stress or shear thinning. But then if you free up these particles, but then again above some stress scale sigma star, turn on friction which constrains sliding, then you can get these flow curves that have a mixture of shear thinning and shear thickening all together in one type of system. And in fact, depending on how you place these different stress scales for breaking and turning on constraints, you can capture many different types of flow curves, capturing a wide array of flow behavior, giving you a general description of these granular suspension flows. And we'll see Louis McHale talk about this in a poster later with a very messy industrial system. And this has also been described in a paper by Ben and James and Wilson and others in PRL. So now that we've talked about the role that particle interactions play, we can begin to move to more complex system. So the first one I want to talk about is a composite of granular particles embedded in a colloidal gel. This is something that comes up very often in industry. For example, in toothpaste, you typically have abrasives in some sort of gel yield stress gel phase. Concrete, you have aggregate in an attractive cement paste, and in making battery electrodes, your active material, your lithium ion, is usually big granular particles in a matrix of conducting carbon black, which forms a colloidal gel. So these are very common. And here you have a lot going on. You have small particles forming a colloidal gel with large particles embedded in them. So we can come up with a very simple model system to study this using two different types of silica: small silica that's attractive with some chemical modification, and large repulsive silica particles. This is work done by Yuji, and what he found is that these composites have some very interesting behavior. So hopefully the movie will play. Not. So okay, there we go. Or not. Doop. Yeah, so this is a vial of this binary mixture that he took off the roller bank, so it's been very gently mixing overnight. You can see as he tips it back and forth, it flows like a liquid. You can see the top surface moving as it flows. But then if he puts it on a vortex mixer for just a few seconds, shakes it up, he takes it off, and then he has a solid where you can see that the free surface doesn't move. It's solidified with just a few seconds of high stress mixing. If we look at the microstructure with a confocal, and we can do this using a confocal rheometer setup that I have at Edinburgh, you can see that what's happening is after high stress mixing, you have your granular particles embedded in a nice uniform percolated colloidal gel. But after the low stress mixing, the granular particles cause the colloidal gel to completely phase separate into these disjoint blobs, and this gets rid of your yield stress and gives you this liquid state. So this gives you a sort of bistable smart fluid that you can control with your stress history. That's really fun to play around with because you can go back and forth between these two different states by applying either low or high stress. So these systems are very complicated. Colloidal gels by themselves are very complicated. So let's turn back to a simpler system where both the small and large particles are repulsive and show shear thickening. So this is thickening shown with simulations and experiments with either all small particles or all large particles. The plots here, we're simply shifting the viscosity by a constant value on this log scale to offset them. But in general, the behavior is the thickening behavior is very similar. It's well described by Wyatt-Cates. The only difference is your onset stress is smaller for the large particles because this onset stress is actually, if you have a constant force, it's predicted to scale as your particle size to the -2. So this here with the all small, all large particles is sort of exactly what you expect. Wyatt-Cates works great, everything's good. But then when we go to the mixtures of the two sizes, we see that Wyatt-Cates suddenly isn't working so well, particularly at these intermediate volume fractions where it really misses the transition, with the thickening happening much earlier than you would predict based just on the simple Wyatt-Cates model. Why is this happening? This is because in Wyatt-Cates, we only have a scalar parameter, the fraction of frictional contacts, which doesn't distinguish between contact types. But what we're finding here with this earlier onset of thickening is telling us is that the large particles, either through large or large small contacts, is playing a disproportionate role in controlling thickening. We see, and so this has been described in a paper by Ben and Chris Ness, along with Jin and Wilson in Soft Matter. We see this again in another type of binary system where we have mixtures of frictional and frictionless particles. As you expect, adding frictionless particles decreases your viscosity, but when we look at how the jamming volume fraction scales with the fraction of frictional contacts, we see something sort of surprising. In standard Wyatt-Cates, the jamming volume fraction just linearly interpolates between the low friction and the high friction limits. But in these mixtures, we find that how the jamming volume fraction changes actually depends on how you treat your mixed contacts. If you say mixed contacts are frictionless, then you get one curve. If you say mixed contacts are frictional, then you get another curve. The fact that you get that there's any difference between these two again says that is a breakdown of the standard Wyatt-Cates. At least a breakdown of the assumption that fractional and frictional contacts is the single order parameter, points to a need for a more complex order parameter that takes into account the nature of the force networks in these grains. So even though Wyatt-Cates works really great for describing experimental systems, it still has some ways to go to really describe these bi-dispersed mixtures. So far everything we've talked about has been steady state rheometric flow. But in industry, that generally isn't the case. These suspensions are being pumped into wells, extruded. So there's you have to think about both time dependence and spatial gradients in your flow. And you might have noticed earlier that there's something funny about this framework for thickening. Everything we've talked about so far has been continuous thickening, where you can smoothly jump from one branch to another below phi m. But if you're between phi m and phi RCP, there you can be on this lower branch, but then if you start to thicken, there's no place for you to go. And this is a recipe for instability. If we take the Weiertz-Cates model seriously in this region, it gives you these backwards bending flow curves where your stress is multi-valued or your viscosity is multi-valued at a given flow rate. So this is something that inherently is going to be unstable. So we're going to see how this manifests. In bulk rheology, what can happen is if you have a rheometer trying to sit at some fixed applied stress, you have to suddenly worry about the fact that the rheometer stress isn't necessarily your sample stress. It also has this plate acceleration that gives you a time scale. And what can happen is, because you have competing time scales for your plate acceleration and the formation of your frictional contact networks, it means that you can start executing these limit cycles where you're sort of looping around your set point on these backwards bending flow curves. And what this shows up as is oscillations in shear rate versus time, where your rheometer is doing sort of this start, stop, start, stop, start motion. And we can actually analytically capture these oscillations with a model based on that accounts for the plate acceleration. Mark Hall at Strathclyde has also been working on a system where he can locally probe stress fluctuations or velocity fluctuations by putting a little like record player needle into his suspension while he's shearing it. And again, what he finds is that if he's, I'm sorry, my...
John, you've got 5 minutes left, including questions. Just
Okay. My keynote appears to have just disappeared. I'm trying to restart it now. I will.
Does Jin have the slides he could do next? Oh, coming up again. Great.
Yeah, maybe Jin should drop back in.
Yeah, I can show the slide if.
Yeah, Jin, maybe you should. I'll see if this. Yeah.
Can you see my screen now?
Yeah, you're on. So we can cut through the extrusion real quick. If you can go to the next slide, Jin.
Yes. There's seems I don't have control. This one. Yeah.
So we can also apply this framework to complex extrusion flows, where a big challenge is liquid migration, where essentially what comes out of your extruder isn't what you put in. Next slide. This is something that can be really problematic in manufacturing. And what we found with extruding a simple model shear thickening system is that we could map out a state diagram denoting where you get liquid migration depending on your flow rate and the size of your die, and connect that to the onset of unstable flow in your rheology. Essentially, this shear rate that you get for unstable flow gives you a boundary in this for liquid migration that allows you to predict the onset of liquid migration with a single order 1 free parameter in your model. So this shows that the steady shear rheology actually can be extended and applied to more complex flows where you have spatial gradients in your stress and shear. And this has been written up by Rory. This was done by Rory O'Neill, and we have a paper in PRL on this. And then I think the next thing is the oscillations. That's back to Jin.
So
yes.
In order to stick to time, Jin, we're going to need to conclude, really.
Okay, so we'll skip this use of flow to control the viscosity. And then this, you can see the paper later on. And then to conclude, so if you like to take one message home from the research today, is that the real small in this very dense suspension or dispersion can actually have a radical effect on the very large scale rheology. So we have shown that so if varying particle friction, adhesion, and repulsion, it can have a dramatic effect. Through understanding this type of particle interaction and coupled to stress and flow, then we are able to predict so this very radical effect, and even some noisy data conventionally cannot be understood in conventional rheology. Then use this to predict a very complex flow. So we hope that from our research, we are providing a set of tools that can be used for formulation and the processing of this type of high solid content dispersion. Okay, thank you very much for everyone for your listening. Happy to take questions, but if there's time, there's no time, I guess.
Well, thank you, John and Jin. That was really good. I guess we could pick up one of the questions just really quickly. There was a question from Tim about the effect that the sort of rule he had in terms of when he was at Albright and Wilson, that they saw dilational effects when more than 10% of the particles were at a 1 to 10 of the bulk particle size, tended to give dilational behavior.
Yes, there's still a shear thickening in the system. So if the particle size are falling into the range of about 10 microns, then the shear thickening can still be seen. So for the mixture of particles.
Okay, right. Well, thank you very much. And there's still opportunities to ask questions in the chat. I mean, I'm sure Jin and John will monitor that. Thank you very much for
thank you.
your talk. And